make this just 15 minutes so I can upload it and you can move through it quickly. So we're looking now at topic 4, which is water and food production systems. We're starting by an intro to water systems. Some of this should be familiar information. So your first job is to find the definitions of the following. Please write them in your own words and make sure they're comprehensible, and we'll share them in the next class. So it's precipitation, evapotranspiration, infiltration, surface runoff, groundwater, and percolation. So these are words you need to know to understand some of the flow within the water cycle. Now looking, we have our water cycle image. You'll notice there's a link, so please do watch that on your own time. This is the water cycle. This should not be anything brand new. We should just be looking at it more with an ESS perspective. So we're looking at these storages and flows of water into different zones, from the ocean to glaciers and polar ice, etc., through the ground, in fresh water, okay, evaporation, etc. And then we're going to think about people's impacts on the water cycle, okay, which can influence the flow and storage of water, and it can also have to do with the pollution and how pollution spreads throughout the water as well. So let's get some basics. This is the Earth's water budget. So the water budget refers to the total amount of water or quantity of water in the storages and in the flows on Earth. So big ideas, well, there's a limited amount of water on Earth, so we're not making new water, okay? So the amount of water there is fixed. There's not a huge abundance of water that's changing. Okay, so it's not being made. That's it. What we have is what we got. Um, Not all the water is usable. In fact, only a small portion of the water is usable for humans. And then water can be considered renewable or non-renewable, just depending on the way your perspective and the amount of time it might take to recharge a certain zone. And we'll look at that in just a minute. So more on the water budget. Actually, less than 3% of the water on Earth is fresh water. 97% of it is salt water. Well, 69% of the fresh water is in polar ice caps and glaciers, so that's not highly usable for us. 30% of the fresh water is in groundwater, and the remaining 1% is in those rivers, swamps, and lakes, as well as in the atmosphere. So this is an interesting way to look at the information. You'll see that the breakdown is a little bit different from what we saw before, but that's okay. It's telling us the distribution of water. So it starts out with the total water, giving us our salt water. So saline means salt. So saline lakes, saline groundwater, oceans, that's all salt. And then fresh water here says about 2.5. Then we zoom into the fresh water and we see what's on the surface, what's in the groundwater, and what's in the solid form in ice. So if we are thinking about what we use, we typically use these two things. So groundwater, surface water. The water that comes out of the tap or the pipe in your house is, in most locations, is actually from the groundwater. Only in few locations is it surface water. So if you live in close proximity to a lake or a river, then it might be from surface water. Otherwise, it's generally groundwater. Then we zoom in from there. We're looking at the surface water. We see that this is actually incorporating both solid and liquid water. So it says surface water. A lot of it is still frozen, even on the surface. Then there's lakes and rivers and swamps and marshes, as well as water stored within organisms, so biological water, atmospheric water, and then it says soil moisture. So that's just the top layers of the soil and how much water is located there. Then Earth's water budget, we can look at this as two ways, sections that we'd consider renewable and other parts that we'd consider non-renewable. And it's based on the turnover time. So if we look, we get a volume of water within these different zones, within these different storages, given as a percentage here of the total water, and then a turnover time. So we're usually focused on fresh water. So I'm just going to say, if we're looking at soil moisture, atmosphere, and rivers, those turn over within a matter of days. So that's definitely considered renewable. Okay, if we take water from a river, if it rains again, it fills up in 20 days. All right, that's renewable. However, the turnover time for some of the sources is extremely slow. So if we are seeing changes within glaciers, So water stored within glaciers or water stored in the ground, that takes hundreds and even thousands of years to replace or to replenish. So that means it's not really quickly renewable, and that's where this non-renewable idea comes into play with the water. So if I pump all of my aquifer, my groundwater from my home area through my well in 10 years, if I did that in 10 years, it takes 300 years to replace it. It's not going to be replaced within my lifetime. So in that way, we're just saying we could possibly consider it non-renewable, though I wouldn't use that as a technical reference. Okay. Then fresh water is precious. We need fresh water. We depend on fresh water for our survival. So 41% of the world's population lives in river basins that are lacking water, so they do not have sufficient water to meet their demands of fresh water and clean water. Worlds are experiencing rivers that run dry, lakes and seas that are shrinking, and falling water tables from overpumped aquifers. So that means that there's disappearing groundwater. Okay. Rivers running dry, one of the examples is the Colorado River. So I'm going to go back home to what I know, but the Colorado River actually flows down the western slope of the Rocky Mountains and starts in Colorado and ends up in northern Mexico. Because the city of did I say it flows down the western slope? I just want to make sure I said that. Because the city of Denver is on the eastern slope, a lot of the Colorado River water has been diverted from the western slope to the eastern slope. So we are essentially in Denver stealing the water from the Colorado River, and then it's drying up as it moves across the southwest zone of the United States. It gets taken by other cities in very, very dry zones of the United States, and it ends up being nothing more than a trickle when it gets to Mexico. So the United States is essentially making that a dry river in northern Mexico where they could have in the past expected water to flow. So how do we impact the water? Well, we know we take it, withdrawals, right? Like you're withdrawing money from a bank. We take it, we use it for homes, to flush the toilet, to wash the dishes, take a shower, etc. Irrigation for agriculture and industries use a lot of water as well. Discharges, so we change water by adding pollutants, sewage, and fertilizers, and this is what we'll be looking at in that like mock or practice IA. The changing flow speed, so we change rivers by, this is canalizing them, so we make them straight so that they don't interfere with construction. So instead of having it wind like a snake, we want it to go straight. We build dams, barges, dikes, just to control the flow, to make sure it's not, flooding certain zones, perhaps. And then we even sometimes take rivers and put them underground. So we might put a big cement tube underground just to capture that water so we don't have to deal with it at the surface. Then we divert rivers, so we try to put them into storages like reservoirs, and we might move them away from a city so that the area doesn't flood as well. So this is the Aral Sea. The Aral Sea is between Uzbekistan and Kazakhstan, okay, which is fairly close to Russia. And you can see over this about 50-year period that the sea has significantly dried up. And the question should really be, what the heck happened to the water? And in reality, Russia took the water. So, Russia, the former Soviet Union, used a lot of the water that would have flowed into this lake, so through the rivers, and they diverted it to irrigation projects. So then water did not make it into the lake. And this is one of the biggest, the biggest lakes in the world in its heyday. And now it's quite dry. So this has left people here with some problems. So they were having some water shortage issues. And unfortunately, the water that's left behind is highly saline, so it has a higher salt concentration than it should. And this goes along with that process of desertification. So this is becoming like a desert region. Then urbanization and flooding. So back in the day, before we had lots of cement and buildings, the water could more easily infiltrate the soil, so percolate through the ground as well, and then be absorbed by trees and all the plants around. And there was less flooding, or less severe flooding. And now we build cities with all the cement, fewer trees, okay, It's hard for water to access the ground. There's not a lot of water taken up by plants, and we are more likely to experience very severe flooding in any urbanized zone. I think getting to our final points, we've got ocean currents and energy. So this is a basic map of the ocean currents. So cold is blue, red is hot, and we see this circulatory pattern of these waters that are cool. Okay, excuse me. Water that's cool tends to be from the depth of the earth, or the depth of the sea, and then heats up at the surface as it rises toward the top in these warmer zones. So we can see areas where the water kind of sinks and cools, and areas where it heats up and rises. And then this reminded me of the Finding Nemo turtle that tells, I think, Nemo and Dory to like surf the East Australian current. So the East Australian current is a smaller current. So these are the big currents, but there is a smaller current of like warm water flow along Eastern Australia, and that's what he was telling. So telling them to do. So here is a link, so you'll have you click that and watch the video when you can. And then back to the ocean currents and energy. So this is like a global conveyor belt moving heat around and moving around the salt water as well. There's a few principles that we should know. Hot water tends to rise. So hot water is less dense and rises. Cold water is more dense and sinks. And then salty water is also more dense and sinks, and less salty water is less dense and rises. So those are just simple principles when we're looking at water circulation. So ocean currents and climates. So we see that water can absorb a heck of a lot of heat. So if you live by the water, you have a more moderate temperature than if you lived in the middle of the land, which kind of reminds me of the Pangea conversation about how the middle of the continent was like crazy hot when it got super hot in the summertime, and then like crazy cold in the middle of the winter. So it's better to live in those moderate temperature zones, and that's temperature is moderated by water. This also happens in the northern European zone. I'm going to go back to the map real quick. So the Gulf Stream carries warm air actually to these Nordic European countries. Nordic. I'm going to go with the Scandinavian countries and the UK just on this western side. So if you look, those countries are actually quite far north, but they have not terrible climates compared to what would happen on the other side in North America, just because that warm energy is brought to that location through those currents. Okay? Whoops. Perfect. So there is a link there that you can watch too on your own time. And then last one, El Nino. So El Nino describes a change in the currents between Australia and South America. So in the normal years, we see cold water moving up from the Antarctic, okay, along the coast of South America and heating up as it crosses toward Australia and toward this Great Barrier Reef that would exist in this zone as well. Occasionally, strong winds cause this pattern to essentially reverse. So then in the El Nino years, we see that the winds are carrying the hot water at the surface towards South America, which creates warmer waters and warmer temperatures in this zone and even up to North America. So that's pretty crazy. So this is El Nino, is just this change in the water currents, and it leads to a change in the climate as well. This is referred to as El Nino, like the boy child, because it usually happens around Christmas time, like December, so it's kind of a like religious reference. And then sometimes when it reverses, so if they have like a really warm El Nino and then they have a really cold reversal, they call that La Nina, and La Nina can bring a lot of nutrients actually up from the depths of the ocean along the coast of South America, which is really good for fisheries. So it's not all bad when it reverses. I couldn't find the Enye, I'm sorry, so it just says El Nino with like a weird N. All right, so have a great time. Please make sure that you're watching the videos and you're also looking at your book for some additional information. Okay, the book is a wonderful resource, so do not forget it's there.